All right, so recapping carbon's average atomic mass. We talked about how if you take a pure element source and analyze it in a mass spectrometer, almost all elements you're going to find more than one mass particle, and that would be related to different isotopes of that element. So the two most common isotopes of carbon are carbon-12 and carbon-13. There is a very trace amount of carbon-14, but you would have to have a really, really sensitive device to even measure it. So a mass spectrometer does two things. It sorts the particles by mass, so we can first just figure out what isotopes are present, but it will also tell you the abundance. So for carbon, almost all of the particles coming through here would measure out as carbon-12, so 98.9% carbon-12. About 1.1% would come out with the mass of carbon-13, and then again, very, very small percentage, like 1 in a trillion, would be carbon-14. So when we look at the periodic table and we see carbon's average atomic mass is 12.01, it's really a weighted average of the two isotope masses, and it's weighted by abundance. So the way that we calculate that is we take the mass of that particular isotope times its abundance as a decimal value, so not as a percent, but as a per 1 ratio. We multiply those together, atomic mass times the abundance. This is the abundance equivalent to 1.1%. And then we add them up, and the sum is going to take into account the relative abundance of the isotopes. Okay. So we're much closer to an average atomic mass of 12.01 because the vast majority of atoms in a sample of carbon are carbon-12. Okay, so we don't just take the straight average of them because we need to realize that most of your atoms are going to be the lighter isotope, carbon-12. Okay, any questions on that? All right, so what I'd like to do on this page is pick another element and do this sort of analysis. And then once we've done that, we're going to break into groups, and each group is going to pick an element of your own and do the similar sort of calculation. What we're really trying to do is understand where the average atomic mass values come from based on isotopes. Okay. All right, so I have a link here. The way this link works is whatever element you put in the address here, it will give you a table of naturally occurring isotopes, and it will give you their abundances. So let me access that link first. So the link I listed had iron in the title. We're actually, I'm going to change my mind. We're actually going to do silicon. I like the way the numbers work out a little bit better. But if we look at iron, what this table is telling me is that there are 4 isotopes of iron naturally occurring. I've got the masses of each with lots of decimal places of accuracy, and then I've got their abundance as a percentage. So we could do it for iron, but I'm going to choose silicon partially because there's only 3 isotopes and the calculation is a little bit quicker. So if you get to this page and you scroll on the left-hand side, we've got an alphabetical list of elements. I'm going to find silicon. And there it is. All right, so for silicon, we have 3 isotopes. The way these are listed here is the shorthand notation for isotopes, where to the left of the element as a superscript, the mass number is listed. If we look up silicon in the periodic table, it is atomic number 14. And the average atomic mass is 28.09. So I'm going to jot that down over here. All right. So we are not going to do iron. We're going to do silicon. And the average atomic mass that we expect is 28.09. And we think of that again as the relative mass. We think of it as the average atomic mass. And we also know that it's going to be the molar mass, the grams of silicon that would have 1 mole of particles in it. Okay. So I'm going to kind of go back and forth between these two pages. So I'm going to list isotopes with mass number 28, 29, and 30, and we'll break down what that means. So 28 Si. And although this page doesn't use it, in this notation, you will sometimes see the atomic number written as a subscript. Silicon is atomic number 14, so I'm going to go ahead and add that to our list of information. And then we have a version of silicon with a mass number of 29. Still atomic number 14, that doesn't change. And then silicon with mass number 30. All right, so just reviewing what that means, right? Silicon as atomic number 14. Every atom of silicon has 14 protons. And what's changing between the isotopes is the number of neutrons. The mass number is the grand total of protons plus neutrons. So these two columns need to add up to give me the mass number. So in silicon 28, we have 14 neutrons. In the isotope with mass number 25, that's 15 neutrons. And then in silicon 30, we have 16 neutrons. So if you ran a sample of pure silicon through a mass spectrometer, you would find 3 different isotope masses. All right, so we need to list the atomic mass and the abundance, and then do our calculation that calculates the average atomic mass. And again, just kind of confirm where this 28.09 number comes from. All right, so like I said, there is a lot of accuracy to these numbers, lots and lots of decimal places, lots and lots of significant figures. I'm going to choose, just to simplify things, and bring over values with 4 significant digits each. So for the mass of this isotope, I'm going to copy it down as 27.98. I'm going to round up. And then same thing down the line. So I'll give you those values. So 27.98. This one is 28.98. And 29.97. Notice that the atomic mass is very close to the mass number. That's because these are measured in atomic mass units, and 1 atomic mass unit is roughly the mass of a proton or neutron. All right, so the abundances, we can write them as percentages. I'm actually going to bring them over as a percentage, and then we're going to turn them into the decimal version of that percentage. So for silicon 28, I'm going to bring over 92.23%. And actually, I'm going to write that a little bit smaller and move it up just a bit, because that's not the version that I want to include in the calculation. Okay. The decimal version of this would just be 92.23 divided by 100, right? That's what percent means. So the number that I'll actually use, I'll use a different color, is the decimal version of that, or 0.9223. So if I carry over those other percentages, again, I'm going to keep 3 significant digits. This one's going to be 4.683%, and this will be 3.087. So 4.683%. The decimal version of that, if I divide by 100, right, I'd be moving my decimal place 2 spaces to the left. So 0.04683. And then for silicon-30, the abundance is 3.087%. And then as a decimal, that's 0.03087. And then again, to calculate that weighted average, I'm going to take the atomic mass and multiply it by the decimal version of the percentage. So I'll write those in green. All right, so I'm going to take 27.98 times 0.9223. And again, I'm going to keep 4 digits in each of these values. So I'm going to write it as, whoops, we'll call it 25.81. We'll round up here. For silicon-29, I'm going to again take the mass of the isotope times the decimal version of the percentage, 0.04683. I'm going to write down 1.357. And I'm going to try to line up my decimal points so that when I add them, it kind of makes sense. We should shift that a little bit. And then my last one, 29.97 is the mass times the abundance as a decimal, 0.03087. I'm going to record this one as 0.9252. I'll round up at that spot. And then to calculate the weighted average, I'm adding all 3 values in this case up. And even before I do it, right, I'm expecting the average atomic mass to be closer to this isotope because it's 92%. The other two will bring the average up a little bit from there, we should see. So 25.81 was the contribution to the average from the lightest isotope, plus 1.357 plus 0.9252. And I get, if I keep all of my decimal places, 28.0922. All right, so if I'm thinking about significant digits, each of these has 4 significant digits, but a different number of decimal places shown. When we add, it's helpful to think of it column-wise. The least accurate term only goes to 2 decimal places. So when we add that way, our final kind of answer should only go to 2 decimal places. So 28.09, that checks out with what's on the periodic table. So I guess what I want to point out with this is when we go to the periodic table and we find an average atomic mass, all of this data is kind of embedded in that number. Okay, so it would be a real pain if every time you looked up an element, you had to look up the isotopes and their abundances. So I wanted to do this exercise so that you know how that number is calculated, where it's coming from. But just realize a periodic table will not show this information. It's just all wrapped up into the way the average atomic mass is calculated. So in fact, no single atom of silicon has a mass of 28.09. But if you have a sample of silicon, even a small amount of grams, you've just got this huge quantity of atoms, and their average, if you worked out their average over across all of them, that would be the relative mass on average. It's also going to be the number of grams in 1 mole of silicon.